Hello all. As I said, we would do another day on L'Hopital's to get that additional practice in. It's nice for limits, it's nice for derivatives. Again, you're doing from 4.4. In this case, 28 is the presentation. So we're going to look at here. So for number 1, the limit of 3, the right-hand limit. And the reason for this is that if you remember ln, if the function natural log can only come from one side for some numbers. And in this case, just as a reminder, just so that we don't have to worry about that, because the natural log has a horizontal asymptote, sometimes you'll see this as a directional limit. When it comes to plugging that in, it doesn't have any actual effect. So the limit of 3, the right-hand limit of natural log of x minus 2 over 2x minus 6. First thing we want to always try with any limit is just try plugging it in. So in this case, ln of 3, you don't need to worry about the directionality, minus 2 over 2 times 3 minus 6. That's ln of 1 over 6 minus 6. The natural log of 1, or the log of anything, is 0. So yep, we have 0 over 0. That means we can use L'Hopital's rule. So in this case, we're just looking at some more challenging derivatives. So the limit part stays the same. And if we remember the limit here, we're going to use the chain rule. So 1 over x minus 2 is the derivative of ln. And then times the derivative of x minus 2, which is just 1, as the derivative of the x term. All over 2 as the derivative of 2x minus 6. Now I'm going to simplify that. I end up with the limit as x approaches 3 from the right of 1 times 1 over x minus 2. So that's 1 over x minus 2. And I usually think about this when I have a fraction in a fraction, as instead of divided by 2 here as times a half. Makes it a little bit easier to simplify. We're considering the limit as x approaches 3 from the right of 1 over 2x minus 4. Now all we need to do, take our x value, plug it in. We end up with 2 times 3 minus 4 under 1. So 1 over 6 minus 4, which is 1/2. So just looking at a couple more challenging derivatives. The other thing you'll see is here is, oh, okay, well this doesn't look like a L'Hopital's problem because it's not a fraction. However, it is still an indeterminate form, because as we approach x approaches infinity, e to the negative x approaches 0, but the root x goes up towards infinity. So if I plug these in, I end up with 0 for e to the negative x times infinity. And if you recall from our last lesson, that's one of our indeterminate forms, because 0 times something should be 0, but infinity times something should be infinite. So the goal is we need to make this into a fraction so that we can use L'Hopital's. Now in this case, I see a negative x. A negative exponent is pretty easy to turn into a fraction. So I'm going to say that this is the same as the limit as x approaches infinity of 1 over e to the x times root x, which is the same as the limit as x approaches infinity of root x over e to the x. And when I plug in infinity here, I do end up with infinity over infinity, because now the power on e is positive. And so then I can use L'Hopital's. So L'Hopital's rule, take the derivative of root x, which is 1/2 x to the negative 1/2, and the derivative of e to the x, which is e to the x. Again, I'm going to do just a little simplifying here, and I'm going to say that this is the same as the limit of 1 over 2 to the x to the 1/2, moving this negative exponent into the denominator here, then times 1 over e to the x, so that it's multiplication instead of division. That's x to the infinity of 1 over 2 to the x to the 1/2, or root x, e to the x. And when I plug in infinity here, I end up with 1 times 2 to the infinity. And this is important. If you have any constant over infinity, that's equal to 0, because what's happening is the denominator is getting bigger, so the number is getting smaller. So like 1/2 is then going to become a third, a fourth, a fifth, a sixth, and all of these quantities are getting smaller, and this whole term then for the limit is equal to 0. So now that you've seen 2 more L'Hopital's problems, you're going to have another problem set to work on. Let me know if you're confused or have any questions, and I'm here to help in the comments, by email, or on Zoom.